Case history number 7 is a demonstration of water cut and flow rate optimization. Let's start with the concept first. We have a downhole optical flow meter, which makes the measurements of velocity, speed of sound, pressure, and temperature. Using these measurements, the optical flow meter outputs the inline and standard phase flow rates of oil, water, and gas. In addition to these downhole measurements, an operator may be conducting surface measurements, for example, test separator measurements. A test separator may be connected to a wellhead from time to time to measure the individual well flow rates. So the main idea of the optimization is to utilize the surface measurements once they are available after the production started. It is then possible to optimize the performance of a downhole optical flow meter. And this is done essentially by optimizing the single-phase sound speed boundary conditions. We will go a little deeper on these boundary conditions now. When we discussed the multi-phase flow measurement in an earlier section, we have seen this plot. This plot shows the variation of the speed of sound for a fluid mixture, in this case oil and water, where the water amount, the water cut to be precise, is progressively increased from 0% on the left to 100% on the right. This curve here is called the Woods curve, and it has two boundary conditions. One of the boundary conditions is the oil speed of sound for 100% oil flow. And the second boundary condition is the water speed of sound for 100% water flow. Between these two boundaries, the fluid is a mixture of oil and water. Now, this plot also demonstrates the importance of the speed of sound measurement, because if the speed of sound of a mixture is measured by the optical flow meter, as shown here by this horizontal black line, then the intersection of this horizontal line with the Woods curve gives a direct indication of the phase fraction, in this case, the water cut. Now, this is the inline water cut for downhole conditions, and it is different from the standard water cut at the surface conditions. The definition of the water cut includes an oil term, and the volume of oil for downhole and surface conditions is different due to the differences in pressure and the released gas from the oil phase. However, it is rather easy to convert an inline water cut to a standard water cut or vice versa through the use of pressure, volume, temperature, PVT relations. In most cases, to determine these boundary conditions is a challenging task. Especially, the oil speed of sound may change significantly depending on the type of the oil, whether it is light oil or heavy oil. So in its normal operation mode, the optical flow meter makes velocity measurement, speed of sound measurement, and it uses the best available boundary conditions, the initial boundary conditions, to predict the inline water cut first, and then it converts it to standard water cut. So if these boundary conditions are correct, The standard water cut reported by the optical flow meter should match the water cut from the test separator. If there is a mismatch, it is most likely due to the incorrect boundary conditions or non-optimized boundary conditions. So let's assume that we have a test separator and the water cut from the test separator does not agree with the water cut from the optical flow meter. In that case, what we need to decide is whether or not the difference in the water cuts is acceptable. Usually, if the difference is less than 5%, it is considered a good measurement for a multi-phase flow. If the difference is more than 5%, we would like to run the optimization process. That 5% may change from one operator to another. Sometimes some operators may have tighter requirements. They may accept maybe 3% instead of 5%. So let's, for demonstration purposes, assume that we have a test separator water cut, and we assume that that water cut is the correct water cut. And the first thing we would do is to convert the test separator water cut to inline conditions. And here is what is done here. We have this blue marker, the inline water cut, based on the surface measurement. And notice that this water cut also intersects the horizontal speed of sound line. But the main problem here is that our Woods curve does not pass through this new intersection point. Now, the main idea of the optimization is to push down this Woods curve so that it goes through this new intersection point, presumably the correct intersection point, and then it will also give us a new boundary condition on the single phase speed of sounds. So let's demonstrate this case. So by lowering the speed of sound of oil at some specific oil speed of sound, this Woods curve, the new Woods curve, will go through the new intersection point. We will call this new curve as the optimized Woods curve and the new boundary condition as the optimized oil speed of sound. Now, note that we have done this process for the oil speed of sound, but we could have done it for the water boundary condition as well. So let's go one step back here. So it is also possible to force this curve down by decreasing the water speed of sound. So at some specific water speed of sound, this curve will be passing through the new intersection point. So it is also possible to optimize the water boundary condition as well. So then, which boundary condition we should be optimizing? Usually, the most common approach is to optimize the oil speed of sound, because the test separator data most of the time is available when the fluid mixture is a two-phase flow. So maybe several months after the production started, and the oil is compressible fluid. It's a compressible fluid, and depending on the type of the oil, as I mentioned, this point may change significantly, especially compared to the water point. So most of the time, the optimization is on the oil speed of sound, but there may be cases, some special cases, that we may also need to do the optimization on the water point as well. For example, sometimes some of the wells may be producing dry oil, especially for their first stage in the production. Dry oil means 100% oil. So in fact, that is a good thing, because in that case, the optical flow meter will be measuring directly the speed of sound of oil. This horizontal line here will be passing through this boundary condition, because the fluid is 100% oil in that case, and this speed of sound has to go through this boundary condition. So once we have that, we have a lock on the oil speed of sound. So we will know that speed of sound with certainty. And after the water breakthrough, perhaps after a couple months, then we can optimize the water point so that we can have both boundary conditions optimized. So this is how we do the optimization on the oil or water boundary conditions. A mathematically rigorous explanation of this approach is in the public domain and can be found in this article here. So now that we have seen how this optimization works without using detailed mathematical expressions, we can go back to a case history here. And we will be using 3 wells from the North Sea. Those 3 wells are from 2 different fields, field X and field Y, and those are generic names for the fields. 2 of the wells are platform producers, and 1 of them is a subsea producer. So we will compare the water cut measurements before and after the optimization, and we will also look at the optimized phase flow rates. This first plot here shows the percentage errors of the optical flow meter with respect to the reference water cut measurements, the test separator measurements. And we have 2 data sets for each wells. The blue square markers represent the percentage errors in the water cut before the optimization, and the green circles represent the percentage errors in the water cut after the optimization. So if you look at well Y1, initially, before the optimization, the error in the water cut was around -8%. And after the optimization we have described in the previous page, the error percentage was brought down to within ±1%. For well X1, the initial error before the optimization was about -3%, which is actually a good measurement, because usually when the error is below ±5%, it is considered a good measurement for multi-phase flow. Regardless, after the optimization, the error was brought down to within ±1%. But the most dramatic improvement was for well Y2. Before the optimization, the error was around 16, perhaps 17%. And after the optimization, it was brought down to within ±1%. So once these boundary conditions, optimized boundary conditions are obtained, the flow meter will be using those boundary conditions and will be calculating the phase flow rates and the phase fractions based on those optimized boundary conditions. And the new values, phase flow rates and phase fractions, should match those from the test separator. One of the advantages of the optimization process is that it is possible to use the optimized values retroactively on historical data. Because The main measurements from the optical flow meter are velocity, speed of sound, pressure, and temperature. Those are good measurements and has nothing to do with the optimization process. The optimization gives us the new boundary conditions, the optimized boundary conditions. So we can combine those optimized boundary conditions with the measurements from the flow meter and recalculate the phase fractions and phase flow rates of the historical data as well. One final point on this slide is about the test separator measurements. The test separator measurements are rarely available, perhaps in the best case scenario once a month, but usually once every other month or once every 3 months. So instead of the test separator, if the well has a surface water cut meter available, that is even better because usually those meters provide real-time data. If that is the case, it is always possible to synchronize the water cut meter with the downhole optical flow meter. We have actually talked about a water cut meter, the red eye near infrared water cut meter, in one of the earlier sections. So in a way, once the downhole optical flow meter is synchronized with the topside water cut meter, then the optimization can be done automatically at regular time intervals. So let's move on to the phase flow rates. In this plot, we are seeing the percentage errors of the optical flow meter with respect to the phase flow rates from the test separator. Now, this time we are plotting only the optimized phase flow rate errors. And the blue markers here show the percentage error in the water phase flow rate, and the brown circles represent the percentage error in the oil phase flow rate. The phase flow rates are calculated using these equations here. So the phase flow rates have two terms mainly. One of them is the Q total, the total flow rate, and also we have a phase fraction function. For oil, it is 1 minus water cut, and for water, it is the water cut itself. So the total flow rate is the sum of the oil and water phase flow rates, and it can be calculated using the cross-sectional area of the flow meter and the velocity measurement of the flow meter. So, in fact, what we are doing here to calculate the phase flow rates, we are distributing the available total flow rate between the oil and water phases based on the optimized water cut value. Now, before I comment on the percentage errors, I would like to point out the differences in the errors between the water cut measurement and the phase flow rate measurement. On the previous slide, we have seen that the water cut uncertainty or the error was brought down to within plus minus 1% for all the wells. Now, that doesn't necessarily mean that we are going to get the same level of error for the phase flow rates. Because phase flow rates, if you look at this definition, also has this second term, the total flow rate, and the total flow rate has this velocity term, which is a measurement with some uncertainty. So it is normal to expect a larger error percentage for phase flow rates because we have two different terms. So let's go back to each well. For well Y2, the error percentage for the water phase flow rate is within 1%. So that's an excellent measurement. For the error in oil phase, we have about -4%. So overall, this point, the phase flow rates here are within ±5% of the reference rate. So that's actually a very good measurement, because anytime a multi-phase flow is involved, usually the ±5% error is considered a good measurement. Now let's look at the well Y1. Both phase flow rates are within ±1% of the reference rates. So this is actually an excellent measurement. And the error here, which is ±1%, is mainly coming from the water cut, the optimized water cut error. So that actually also tells us that Q total flow rate for this well must be spot on. So we have a very accurate velocity measurement for this well. So let's look at well X1. We have an interesting situation here. Now, the oil error is right around -3%, so it is within the band, within the ±5% band, but the water error is outside the 5% band. Also, one thing that we should notice here, both of these phase flow rate errors are on the negative side of the 0% error line. This is not the case for the other two wells. So remember that the water cut error on this X1 was only within ±1%, as we have seen on the previous slide. But here we have larger errors. So that actually tells us that that error must be coming from the total flow rate measurement, the velocity measurement. So the optical flow meter is actually under predicting the flow rates, the total flow rate. So there must be an issue with the velocity calibration at the factory level. And that's actually an easy fix, because we can actually add an offset to these phase flow rates and bring these errors to both sides of the 0% error line. So now, the fact that we have these larger errors can be corrected, but I wanted to leave it that way for demonstration purposes to show the differences between these measurements. We have now completed the video series on optical flow measurement and its applications. Congratulations on your fine achievement.